Introduce our second last speaker, Eric, who's going to speak to us about antisocial behavior, which I'm sure that some of us know a lot about. He's going to place it under the microscope, tell us new, wonderful ways to be antisocial.
Oh, goodness. All right. After all that, I'll have to see if I can live up to the expectations. Can people hear me? Is this in the right spot? Yeah? Okay. All right. I like to get my collaborators and support right out of the way. Otherwise, I get caught up into what I'm talking about and I forget by the end. It also is good for setting context. So this is joint work with Mark Cravella and Paul Barford. They're responsible for the computer science and networking side of it. I do my best to keep up with that. I'm a statistician by training. Ki Ding and Natalia Katenka are a student and postdoc of mine, so they also have primarily a statistical perspective. Let me give you a little context on the problem, and then I'll start sort of drilling into what we've been doing on the problem. I'm going to preface all of this by saying that despite being a statistician, despite my favorite sort of problem being the one where I have some interesting math hitting right up against to an interesting disciplinary problem, there's basically no math in this talk. Even the statistics is fairly low level. There's a lot of thinking about the data and the processes and about trying to navigate ourselves to a useful context for the problem that I'll show you in a moment, so that we can use that as a leverage point to some of the more interesting statistical and mathematical problems that we have felt are there. So I'll mainly show you the data and the problem and what we've done exploring it, and then I'll spend some time at the end talking about what I think are some of the more open problems, a number of which we're working on. Okay, so the goal at a very high level is we'd like to detect malicious network activity from NetFlow records, of which Matt and Anna already talked a bit about some of those things. We'd like to do it at the level of IP addresses, and we'd like to use fairly minimal levels of information. So in particular, we're not interested in deep packet inspection. We'd really like to use just what's in the header of the packets and flows going by. All right, so the idea here is there was a pointer at some point. No? Okay, well, I have a pointer. I just brought it. Right? All right, so the idea, the antisocial behavior, right, well, I'll watch from that. The idea is that if this particular, this is an old diagram, so I didn't get in and try and wordsmith out the words. If this is a source and it's sending traffic towards various destinations and it has some sort of malicious intention to them, it's an attack or it's seeding viruses or whatnot. If we're sitting in the middle of the network, right, perhaps at a point of presence, a POP, right, or a collection of routers, and we're watching all this data flowing by, we'd like to be able to identify that this IP is engaging that behavior. And the nuance here is that this is part of a larger project with Mark and Paul, in which we're particularly focused on wanting to be in the middle of the network, right, as opposed to being on the edges. So we're envisioning massive amounts of data flowing by, right? And this would just perhaps be one needle in a haystack of data that's sitting out there. What kind of activity is of interest to us? We might be interested, say, in the context of email, of spamming or phishing. HTTP, maybe planting drive-by malicious code on servers, DNS cache poisoning, various, the RIAA, I can't remember the acronym, the Recording Industry Association of America, I think is RIAA. So folks who have vested interests for file sharing, peer-to-peer type applications not being abused for copyright protected material. We're a little less interested in older style type attacks, ones that are more like a sledgehammer, massive denials of services, large scale worms. We're interested in things a bit more subtle here. And we fall within one of what I would say are two broad, and of course I'm being general, areas for detection. Right? Broadly speaking, we'd say there's sort of misuse detection and anomaly detection. We fall really in the anomaly detection realm. What we're calling misuse detection here are methods that are, say, signature-based. Right? They're relying on some sort of predetermined features or patterns, and then you're matching that in the traffic. Right? They often require deep packet inspection. That's something we said we'd like to try and avoid. And if there is that information in there and you pull it out and it matches its signature, then you'll do a good job with it. But if there's something new that's a perturbation on that, then it may be relatively ineffective for trying to identify whatever is the new type of attack until you know the signature. Right? The other end of the spectrum, you have so-called anomaly detection methods in our choice of taxonomy here. This is relying on some notion of normal, and so anomaly is something that's not normal. The challenge here really is trying to effectively formulate what you mean by normal. Right? It has the advantage that for things that are unanticipated, that you may not know that this is coming, it may stand out still as abnormal in the way you've defined normal, and so you may still be able to detect it despite not knowing some sort of specific signature. We're going to stay in this area here, and we're particularly interested in trying to define our notion of normality within the context of a representation of the social behavior that is behind the transmission of the traffic. Okay. And most of what I'm going to show you is really our efforts to try and structure that. Right? This is a very vague sort of statement. Right? Here's a start at it. Right, so we're going to take as a definition intrusion as an act of entering a community, and I probably should put community in quotes, right? I'll give it air quotes there. Right? The act of entering a community to which one does not belong. Right? So at some intuitive level, and there's literature on this for certain types of traffic, right? People have noted this. In fact, this type of thing has been noted in various types of contexts. So at some rough level, this seems to make sense. The observation would be that malicious activity represents an act of intrusion. And if you're a malicious source, then perhaps within the right representation of the network, the social behavior, and the communities, these would stand out as exhibiting what I call antisocial social behavior, in the sense that they are interacting with those communities, but they're not belonging to those communities. So they are socializing with, but they're not social members. Right? So this is suggesting an approach based on social networks. And what we're going to look at is trying to characterize what we see in a certain set of IP traffic data, and then see if some of the characterizations that we find can be used for very simple detection. Right? So again, most of this is really proof of principle work. There's certainly lots of previous work. This is by no means exhaustive. We don't know of any work that's putting all the elements together that we are on this particular problem, but certainly there's work putting various subpieces of these things. So work by Shili Zhang and colleagues at Minnesota has been aimed at what they call traffic activity graph decompositions. They form something similar to what we call bipartite flow graph that I'll show you a little bit later. And they look at the composition in those graphs of certain types of traffic behavior. So what does HTTP look like in these graphs? What does DNS look like in these graphs, etc. There's a small literature on the identification of high activity hosts for the purpose of detection. Right? There's something about the fact that they're simply involved in very high activity that can be used for detecting. We'll come back to that as well. There is the use of cluster and rule-based non-social intrusion detection on graphs. So using graphs and using notions of clustering / community detection and rules to do this intrusion, but the graphs aren't social-based. And then finally, there's general graph-based anomaly detection. So our work is differing from these in the extent that it is combining various pieces of all of these in the context of a problem that hasn't been looked at with these. All right, so here's an outline of what I want to do for the rest of the talk. I'm going to start with the description of the data. I'm going to give you a sense as to what aspects of the data we're going to pay attention to and what aspects, knowingly for the moment, we're going to ignore. And that's important when we come back at the end for assessing the methods. And then we're going to go to the important context of network representation. So we're going to take a social network perspective on attacking our problem of detection. The question is, what network are we using? We're not using the physical or logical topology of the internet itself here. Right? We're going to try and form a social network from these measurements and then see if within that social network we're observing some of the structure and behavioral characteristics that I was talking about. We'll talk a little bit about that by talking about the context, the particular question of characterization. I'm going to look at a very simple attempt at community detection. We're going to look at the notion of cut vertices, and we'll look at some local structural characteristics. And our reason for choosing these three is they have different strengths for being able to pull out this antisocial social behavior. And then I'll show you how using some of the statistics that come out of this work with detection. All right, so here's a quick description of the data. We have net flow data collected at a single router in a large European ISP. We have 2 weeks of this. This is non-anonymized. This is in May 2007. Most of what I'm going to show you is one-day results for May 1st. Right? My understanding is this has 1 on 1,000 packet sampling. We have roughly 30,000 source IPs in a given day, sending to about 200,000 destination IPs, a total of about 2 million flows. So that's roughly the volume of data we're working with. We will typically use subsampling in the results that I've shown you to reduce that down to about 10,000 source IPs and their corresponding flows and destinations. That's purely just for our computational convenience. In talking about malicious behavior, we'd like some kind of truth set. Right? And we've had a lot of discussions about truth sets and the ability to get truth sets and the quality of those truth sets. This is also an area where it's hard to get truth type data. What we're using here is a set of logs from so-called DShield software from the SANS Institute. These things collect information from firewalls and intrusion detection systems from about 1,700 networks worldwide on intrusion attempts. Right. We're going to have, for the period that we're looking at here, about 300 to 400 source IPs, depending on the 300 to 400 source IPs, depending on the day we're talking about in this period, sending about 400,000 flows to about 67,000 destination IPs. Okay, so this will be what we'll use as we're going through forming a social network from this network flow data, marking some of the points with IPs from this intrusion data set, taking them for the sake of discussion to be malicious. Right? This will not be exhaustive, of course. And then the discussions that we have regarding where are the malicious nodes sitting, can we find them, etc., is with respect to this data. Okay. All right. So Walter obviously was a stickler for a number of points regarding the analysis of this type of data. Power law type graphs, getting to know your data, paying well attention to what it can and can't do. I'm a stickler for defining your networks. Right? That's one of the things that really gets under my skin, is when someone comes up and you start showing pictures and they start showing results and they've never actually told you, other than saying the network, what they really mean. Right? Most of what we're doing here, because we started with a basic question, not with a network and went running with it, a lot of the work is really thinking about what network do we want here. Okay, so that's what the majority of the next 5 or 6 slides are going to be. Right, so our hypothesis here is regarding intrusion based on some notion of social interactions. So a network would seem to be natural here, and the question is really which one to use. A common choice to begin working with flow data has been with a bipartite graph representation. Right? So we define a graph that has 2 vertex sets, V and U. V is the source IP vertex set. Every single one of these nodes represents a source IP. In principle, there's 2 to 32 of these things. Right? U is representing the destination IPs. Of course, they can be the same. So in principle, we have another row of 2 to 32 of these. In practice, with our data, we tend to have, as I was showing you earlier, a smaller set of sources in the tens of thousands, a larger set of destinations in the hundreds of thousands, And interestingly, in our data, not a lot of overlap. Right? So it does it does roughly match up to 2 disjoint vertex sets. An edge going from a vertex V, which is a source, to a destination U being a destination, that will indicate that there was a flow from V to U, right? So there's a flow record in our data. You can handle multiple flows in various ways. When I show representations, I'm going to show just a single edge and then put a weight on it according to the number of flows. All right. So here's a running illustration that I'm going to use throughout the talk. Right? So this comes from our data. It's a little teeny snippet of the large bipartite graph that we have from the first day of our data. It represents 25 flows sent from 10 sources to 4 destinations. Right? And we took this because it represents the point that we were interested in looking at. Right? So if you focus on, I'm not sure to what extent you can see numbers, but number 9, right above my finger here, right, is sending a flow both to destination A and to destination B. Right? On the other hand, you also have sources 10, 1, 2, and 3 also sending to destination A, but that's it. Right? So this is just a toy. And over here, we have a slightly more complicated picture of 7, 4, we never did figure out a right way to organize our vertices here. 4, 5, 6, 7, and 8 are all sending to B, C, and D, and 9 is also sending to B. Right? So at some rough level, if we didn't have any context here, right, we might look at it and say, well, those ones on the left there seem to have some common reason to be sending to A. Right? And some of them over here have some similar common reasons to be sending to B, C, and D. And then there's certain nodes like number 9 that are sending to multiple ones. And it doesn't mean they're malicious. Right? This could be going to a web file server and then participating in some kind of file sharing. And it could just be that here's one place and here's another place, and that person in number 9 was participating in both. But our idea is that if at certain resolutions, we suspect that people who do have that type of behavior probably are malicious. Right? Not all of them, but some. So we're going to take that bipartite graph then, and we're going to turn it into a single one-mode graph. Right? So the bipartite is defined on a set of vertices that are sources and a set that are destinations. We're going to concentrate just on sources. We're going to see to what extent we can get some mileage out of creating a source graph. And we're going to do it from the bipartite graph using 2 approaches. Right? One is going to use the standard so-called projection of the bipartite graph. And another one's going to use a more sophisticated notion based on random walks on the bipartite graph. It uses a tool called SimRank, and so we call this a SimRank projection. Right? There are lots of ways you could think about creating a one-mode graph here. This is our attempt to kind of get 2 somewhat distinct approaches to it in a way that I'll explain. All right, so the traditional one-mode projection is a graph with the vertex set V now, but an edge set EP, where sources VI and VJ are connected if and only if they share at least one common destination. Okay? So you take the incidence matrix, you multiply it by its transpose, and then you apply a binary operator to that. Right? That's it. Here's what it looks like on our toy. As I said, I'll keep bouncing back and forth with the toy. Right? So here's the bipartite graph. It's a little smaller now. There's our node number 9. Here's its cluster of 1, 2, 3, 10. That get mapped over here. There's 1, 2, 3, 10, and 9. They form a clique because they all commonly participate with just this one destination here. Right? So by the rule, each of them are going to be linked to each one of the others. Right? So that act of commonly sending to this destination creates a clique under this way of defining a source graph. Similarly, over here, we have 4, 6, and 7. Right? Those are also sharing with 9 a destination, but they share multiple destinations. Right? And then finally, we have 8 and 5 over here. Right? And so the main thing I would note with this is that although this is sort of your first knee-jerk way of creating a one-mode graph from the bipartite, these types of nodes here end up having a certain character. Right? The fact that they stand out there means that they end up being the nodes that are connecting these groups, being between these groups. And that was capturing our notion of antisocial social behavior. Right? So 9 is in this group. Right? 9 also, in some sense, is forming this triangle here. But these ones, who are only communicating with that vertex A, they're not part of the rest of them. All right. That could be a little too simple. Right? In fact, it probably is too simple. Right? In the sense that we're connecting these sources really only through their one-hop neighborhood structure on the bipartite graph. If you've talked to anyone common, we link you. Right? That may be too extreme. Right? So we thought about other ways you might want to do this. And one way is that what we really wanted to capture was, without having the temporal data, right, because we've collapsed everything across the day, is the idea that perhaps I communicate with the destination, right, and another source communicates, right, and that leads to communication between this source and another destination to another source. And so there's sort of a propagation across the network that you could picture the actual social activities behind these flows encompassing. Right? You could picture a social activity that actually was encompassing a number of these links, linked in some kind of local structure. Right? And so we wanted to capture that. And the SimRank algorithm was an algorithm that was proposed that we're sort of adopting to do a certain calculation. Right? So I won't go into what the SimRank algorithm is doing, but the calculation that we get out of it is the expected waiting time to go from one source to and from another source and to meet if you do a random walk. So you take your bipartite graph, you start at one source, you get a particle going on a random walk. You start at another source, you get a particle going on a random walk. You look at the expected time until they meet. Right? You take the inverse of that, and we use that as a measure of similarity. Okay? And that's what we're calling a SimRank similarity. The more destinations you're sharing, right, the more opportunities you have for these random walks to bounce up and down and meet somewhere. Right? If you take the extreme and you have a destination here, a source speaks to it, another source speaks to these destinations, they don't overlap at all, those random walks will never meet. Okay? All right. So we get a fully connected graph, but it's weighted. And this is the type of thing that you get, right? So this is the same bipartite flow graph. Now we see that where we had this group of vertices 1, 2, 3, and 10, and 9 over here, right, they're not broken off from the other graph, but they have stronger similarity amongst themselves than the others. Right? On the other hand, we have this characteristic that everybody has some similarity to each other, right, which perhaps is beginning to blur the picture. Right, so we played with other formulations. There's lots of, you could spend a long time just playing with how to define these graphs. But we played with these two because to us they sort of represented two nicely defined extremes as to how you might talk about linking sources. All right, so here's a question. Now that we have a couple graphs that we're going to use to capture from the data the notion of how the sources are interacting, how does the status of non-malicious or malicious relate to the relative position of these sources within the graph and perhaps the local or global topology? Right? Is there something about where you are in these networks that is at all indicative of being malicious? Right? Or are the networks pretty much unrelated to that? So we're going to look at three ways to explore this. Right? One is with the community detection algorithm. The second is with the use of cut vertices. And then I'll talk about a few standard statistics describing local network structure. All right. So we applied the Closet-Newman-Moore community detection algorithm. A couple people have mentioned this as well. We chose it because it has the reputation of pretty much a standard. This is a modularity-based algorithm. We worked with the largest connected component of the 10,000 node source graph that we had for day one, so it's about 8,500 source nodes. On that graph, we had 161 D-shield nodes. Right? And then there were 24 singletons that stood out alone, right, that we're not using. Right? When we optimized the modularity, what we got was the following. This 8,500 node graph gets broken down to a single giant connected component of about 6,800. Right? Another large one of about 1,000 nodes, and then a handful of smaller ones, and then about 50 tiny ones. Right? And the point of the table is to look over here. Right? So where were the D-shield nodes? Where were these ones that were identified as malicious by the D-shield system? Right? Out of the 161, 158 of them were buried in this largest component. So the point here was that by doing at least an off-the-shelf type of community detection, it's not breaking it up into pieces that somehow are helping you separate out these nodes. They're still buried. It says cut it up into this big piece, another big piece, and a few smaller ones. And the majority of them are just all buried in the big piece. Okay. This goes very much to the heart, I think, of what Michael Mahoney, for example, was talking about in his talk yesterday. Right? It matters what you mean by community. It matters what you're looking for. Right? It matters, therefore, what algorithms even you use, and et cetera. So we purposely just took it off the shelf and tried it here. Right? This is saying the same sort of thing, right? We're trying to seek a highly parsimonious partitioning using modularity, right, based just on the graph topology. These so-called communities are really not nearly sufficiently fine-scale to distinguish where the malicious, non-malicious are. Okay, so they don't go together. Right? It's possible, I guess, you could try some sort of non-optimal levels of modularity. I'm not sure how one would want to try and do that. My preference would be to rethink what I mean by going after communities rather than trying to tweak a single tool. Right? So what we did is we explored a different approach, and one that was very much driven by this notion of being antisocial social. So we expected that this is quite possible that these things would not pop out. Right? So what we did instead was look at the notion of cut vertices. Right? So if we go back to the diagrams that we've generated, right, we have this bipartite toy graph, and the one-mode projection, if we'll just concentrate on that, right, was like this. And we already commented how this thing was sort of at the edge of this group and these groups. Right? So it suggests, for example, that if we just remove this vertex, then we'd actually disconnect the graph. Right? And so it suggests that maybe where these things are is actually in so-called cut vertices, or sometimes called bridge nodes. And so we're going to do a very simple experiment, right? And we're going to try and see, are these things in the language of biology, which is another group I sometimes collaborate with, are these cut vertices enriched for malicious behavior? All right, so here's our algorithm. Right? We're not trying to be smart about this at all. If this hadn't worked, maybe we would have been smarter, but this already worked. So we start again with this largest connected component of the one-mode projection graph. We identified all cut vertices using standard Maxwell-Min cut type algorithms. Once we've identified them, we remove them, and pieces drop off. Okay? We take the largest piece remaining. That's why I say this is not smart. It's just drilling away. And we do the same thing. Another piece drops off. Take the largest one, do the same thing. When we finally end up with a largest piece that doesn't permit us to find any more cut vertices, we stop. Okay, so we haven't tried to go find all the cut vertices. We're just trying to greedily knock off cut vertices. Right? We iterated until that 8,000 node graph ended up being about 4,600 nodes. About 50% dropped off. And I think I remember Michael Mahoney actually talking about similar types of numbers with a similar type of algorithm. All right, so here's a question. Are these cut vertices enriched now for D-shield sources, meaning are there more of them within these cut vertices than you'd expect? Right. So the output of our algorithm was 1,303 nodes. Right. 86 of these were D-shield nodes. So that's about 6.6%. And you figure, well, that's not a real big number. right? 6.6% of the loop. But remember, we weren't trying to be clever. We were trying to get all cut vertices. We were just knocking things off. Right? If we randomly reassign 161 D-shield labels among these 8,500 source nodes, right? And we do this, so we rerun the algorithm 100 times, right? And we say, now what percentage of these cut vertices are the so-called D-shield nodes? You only get around 1 or 2%. Right? So it's a crude, quick, back-of-the-envelope proof of concept here that the D-shield source IPs are highly enriched among these cut vertices. And so it suggests that our hypothesis of antisocial social behavior among malicious sources in these graphs is somewhat supported by this data. All right, so we looked a bit beyond cut vertices for a couple reasons. Right? One is that I brushed it under the table, but I said I'd bring it back, right? Is we have sampling here. Right? So we have net flow sampling. Nick talked about a variety of more recent algorithms, but there's also just the basic algorithm that he was building on, right? 1 in 1,000, right? Watch the packets flow by, bop, 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 right? That has a certain type of bias. Certainly you're going to miss some flows, and in fact there's a bias as to what flows you're going to get, in the sense that there's a length bias. Right? The longer flows, you chop them up into a bunch of packets, you have more chance to have seen that flow. And an arrow in our bipartite graph is simply representing that we saw the flow. So we'll be missing flows, and in fact there will even be a bias to those flows that we're missing. Right? So if you have a cut vertex which somehow is much less connected to the graph than other ones, and perhaps even it's a vertex that maliciously is sending very small levels of malicious traffic, then you'd figure that you may be missing some of those purely due to sampling, and maybe even disproportionately missing them. Okay. So we were leery of going to go too far with cut vertices. Right. The second reason is that we also have, I haven't been emphasizing it and I won't for most of the talk, but we also have this weighted graph, the one from the SimRank algorithm that was attempting to link sources based more on their local communication structure. Right? So that's weighted. Right? At least the basic notion of cut vertex we're using here, simply take it out and it drops out, that's not going to happen. Right? We could use some things more complicated, but at least at a first cut, that's not going to extend. So we said, well, all right, how about we look instead really at what's going on locally? Not simply that the vertex, when you take it out, it drops off components, but really what's going on locally in terms of structure. And there's two very natural things to look at here, right? One is clustering, and the other is betweenness centrality, and I'll explain both of those. Right? So for each vertex I, we computed the local clustering coefficient Ci. Right? This is just the proportion of connected triples. You have you have a vertex I here, you have two other nodes, they happen to connect, and you ask yourself, is there a link there, right? The proportion of those things that close, that's your local clustering coefficient amongst the triangles that are rooted at I. Okay? There's a weighted version of this. There's actually a few weighted versions out there from what we can tell. Onella and colleagues have one that we used, and they call it intensity. So betweenness is the other thing we use. Right? Betweenness centrality is one of sort of a large literature of centralities. I mean, it's almost a cottage industry out there. It's amazing the variety that they have. All of these centralities are trying to talk about the importance, quote unquote, of a node in some sense. And it's the difficulty of capturing what you mean by importance that has led, I think, to so many versions of centrality. One of them out there is betweenness centrality. What that essentially is doing is saying, for this node, if I look at pairs of nodes, is the shortest path between those pairs going through me or not? Right? And then you ask that for all pairs. Right? If it's not a unique shortest path, then you end up having to use sort of a weighted counting. If they're unique shortest paths, then you're really just counting the number of shortest paths that go through you. Right? For the, let's see if I had the picture there. Yeah. So for this graph, right, you can picture that among these, for example, these two connect to here, that triangle, that triad is closed here, right? This connects to those two, that's closed here, right? Within these communities, because of how we form this graph, right, where those communicating with the common destination are forming cliques, you're going to expect that you're going to have high clustering coefficients for those that are within those communities, quote unquote. And likewise, for those that are participating but not necessarily members, you would expect that oftentimes you're going to get that triangles like this, for example, are not closed. Okay? Similarly, in terms of betweenness, if you ask for a pair of vertices, does the shortest path between them go through this one or that one or that one? No. But a lot of them will go through these because they form sort of bridges between the groups, and you're going to have to funnel a lot of things over. Right? And so what we have is some numbers up here looking at the vertices 1 through 10, and for these graphs looking at clustering and betweenness in the top row for the projection here, and in the bottom row, bottom two rows for the sim rank. And what all of them are doing basically is suggesting that it is vertices 7, 8, and 9 in which are standing out from the others. Right? Sometimes stand out as larger than the others, sometimes stand out as smaller than the others. Okay. All right. So we took that basic idea from the toy and we said, all right, in the data where we've constructed these graphs now on a large scale from the flows, right, what happens if we look at these statistics? These are vertex-specific statistics. What happens if we look at them and average them just over the D-shield nodes, right, the ones that were identified as malicious, versus averaging them over all of the source nodes? Okay. And again, the main point of the table is to show that these numbers stand far apart from each other, right, which is suggesting then that there should be some hope of doing some detection based on even just these very basic statistics. Right. Now all of this, again, as I said at the beginning, this is it was somewhat a long going, but preliminary still work compared to where we want to go. Right? This is very exploratory. There's a variety of interesting problems. I'll get to them at the end. One of them is how to build a good, clever sort of detector. We haven't tried to be good and clever here. We've taken the basic statistics we have here, right? And we said if we compute them and we threshold them, how do we do in detecting the D-shield nodes? That's it. So I have a couple sets of results. A bunch of them are for 1 day, which is basically what I've been showing you most of the talk, the May 1st data. Right? And then there's a couple ones that show the robustness of these results over 2 weeks. All right. So these are ROC curves. Right? This is showing a false positive rate and a true positive rate. This is a standard sort of diagram. The curves are being carved out, for those of you who don't know these types of curves, as you vary the threshold. Every curve corresponds to a single univariate statistic, right? So I calculate that statistic for every single vertex. I line them up, right? I sort them. And I run a threshold down them. Some of these are marked as D-shield, some are not. And I'm looking at if everything below the threshold is declared malicious, then what's the false positive and true positive rate that I have? Okay. The idea is that optimally you want to be in the upper left-hand corner, where you have the 0 false positives and 100% true positives. Right? Random coin flipping would be a line going from this corner to that corner. Right? So you hope your curves are above the diagonal, and you like them to be well above the diagonal. Right? And we have results here for both the sim rank graph and for the one-mode projection using both clustering and betweenness. Right? And what you see here is that the one-mode graph, somewhat to our surprise, is performing noticeably better than the sim rank graph using the same types of statistics. Right? They have an area under that curve, right? Ideally, you'd have a 1.0 area on the unit cube there. And these have an area under the curve of about 0.8, which is reasonably good. Right? The other thing we've shown here is this dark line, which is the one that runs along the top and pretty much parallels our betweenness and clustering. That's using a very simple identifier for detecting maliciousness. It simply says, did that source send out a lot of traffic? Right? Did it send out a bunch of flows in the period we looked at? This is connected to one of the literatures that I pointed to way at the beginning of the talk about high activity sources. Right? And we find is that also is doing pretty much as well, if not a touch better than the two that we've looked at with clustering between us. Right? So the question there is, so we don't need any social behavior or story or anything like that, and Eric has wasted our time for the last half hour, right? So we took a look at that. This is a plot of the clustering coefficient from 0 to 1 versus log out degree. So this is the statistic that's being thresholded for the high activity literature. And this is what we're thresholding, for example, with the clustering, right? And that's based on these social ideas. Right? The blue notes, I know these are hard to look at. Right? A number of speakers had commented, so I was up here before while you were all drinking coffee, looking at each of my plots going, oh, shoot, oh, shoot, oh, shoot, right? All the things are going. So this is going to be a little hard to see here. But there are blue dots and there are red dots. All right? No? No? Okay. Okay, well, Daryl can see it, so he's going to keep me honest. Otherwise, I'd have a really good story about where the blue and the red are, right? The red dots are kind of sprinkled throughout. You can see there's more of them up here for those who are in the back, right? Because it's a little sparser, and they tend to outweigh the blue by a bit, right? This is corresponding to this idea that high activity is often associated with certain types of malicious behavior. But on the other hand, there's a bunch of red dots here too. Right? So this is lower activity. Right? Also has zero clustering. So you say, okay, you sort of start working those things backward. This corresponds to sources who communicated with destinations that nobody else communicated with in our data. Of course, there's sampling issues, right? And they didn't necessarily correspond to as many as some of the sources in the database that were malicious. There's other ones, like these, who have a very high out degree that communicated with many, many destinations, right? But are engaging in very much the type of antisocial social, or exhibiting, I should say, very much the type of antisocial social topology within this graph. Right? And then as you go on, you can find that even amongst the very low out degree, there are some that have very high clustering. So they're not exhibiting the behavior we have. Right? So the story to take away from that plot really is that, that it's nuanced. It isn't an issue of high activity being the right way to do this, or the social being the right way to do this. Right? There's quite a bit going on there. This is a little different way of looking at this. If you look at a false positive rate of 10% or 20%, whoops, not 200%, 20%. And you look at the clustering or the out degree, and you say, how many positives did they have? Right? How many detections did they flag? Right? How many of them were true? How many of them were false? And then amongst the number total, the true and the false, how many of them did they both identify? Right? That's what that's okay. It's just a Venn diagram. Okay. And what we're seeing here is that among the true positives, right, and among the positives here, right, we have about close to half that are common. Right. We have a higher percentage of the trues that are common, right, and a lower percentage of the falses. So they tend to be picking up more common trues, but among the falses, they're making different types of mistakes. All right. Daryl's standing, so I know what that means. I'm going to move to the 2-week analysis here. This is really just showing you that you get similar types of curves if you just look at this behavior across the 2 weeks and you say, how do we do for identifying them on a daily basis? If you look on a daily basis, we found that actually those that were in the D-shield logs did not tend to persist for a long time across each of the days. Right? So if you look on a daily basis, you see that the relative comparison of these methods is still quite similar. There's a little bit of variations in there. The error bars on those averages are quite small. So let me just finish up here with the discussion. To me, the discussion is sort of really, this is where we're at. This is what's really most interesting. I've been talking to a few of you here about individual tools and topics related to where we're going with this. The work here suggests there is definitely potential in a social network approach to this anomaly detection-based intrusion detection. There's a lot of work to be done still. Some of it is still very much empirical, and some of it is mathematical. And there's some interesting mathematical questions here. The incorporation of application-based information here could go a long way. And there's a couple plots I skipped over there where we're beginning to take a look at some of the sources and ask what sort of ports were they using. Right? There's a bunch of these D-Shield ones are using port 0. Nobody should be using port 0. Right? There's a bunch of them they're using port 53, right, for DNS. So you can do that analysis, and we're starting to do that. The question is whether there's anything identifiable out of that. Right? Moving beyond the nodes, you can ask, are there motifs in these social networks that seem to correspond to certain types of applications? Right? So Zhili Zhang at Minnesota, as I said, has a couple papers where they've done some nice work more on the edge of the network rather than the core where we are, but doing this type of thing of asking, if you just look at flows of a certain application type, what do you get in terms of network structure? In terms of the mathematics, we've got two directions we're looking at. I should probably switch these because this one we've started and this one we're just started. The implications of net flow sampling on the network topology. I took the opportunity to corner Nick earlier today and sort of say, tell me where things are at with this area, because I know there's work out there where people have looked at the implications of net flow on both very simple characteristics. There's someone at UCSD, I believe, who's done slightly more sophisticated things like traffic matrix estimation. And there's work out there. I'm not sure if anyone's looked at this problem of what is the particular implications of the particular size bias sampling that you have on the formation of the topology of these graphs we're doing, and then propagating the uncertainty in that to our statistics. So in other words, what's the implications of net flow sampling on using something like a clustering coefficient of the particular one-mode projection graph to do detection? And that's something we're beginning to look at. The last thing is we did get some nice leverage out of these social networks, and you begin asking yourself, is there anything with the topology of these things that relate to the spread of viruses and similar? And so we've just started some joint work with Tom Britton at Stockholm University on trying to take the bipartite network and talk about what implications that may have on propagation rates between pairs, map those onto the social network, and ask ourselves, is the location of whether you have antisocial social behavior or just being in a community, to what extent is that affecting the propagation of a quote-unquote virus? So, and I'll stop here.
Running late, I think we should take at least a couple of questions.
You mentioned that there are several interesting mathematical questions. Could you just mention one?
Sure. I think the one that's most interesting to me is asking questions of the simple sort would be, what is the distribution of a degree in our one-mode network under a very simple model of net flow sampling that produces the bipartite graph that we produce that one-mode network from?
So that you could then check against.
So you could have an understanding, for example, of what are the implications if sources of a certain type, the so-called malicious, have certain flow characteristics, which are what's directly attached to the bias sampling. So is there a connection between how you interact in the network and whether or not you're seen in the network and how you're seen in the network, as i.e. being well clustered, being not well clustered? We can talk afterwards if you like. Yeah, Walter, please.
So, what about the time window? So, why are they discrete?
Good question.
Do you see sensitivity to if you, let's say, if you do an hour? I mean, it's all a question of aggregating. The longer the window, the more flows you see potentially going
Right. So we have looked on the larger end of that, right? We looked over multiple days there and saw that there was fairly consistent behavior. We haven't drilled it down smaller to ask sort of where does it break down and when and whatnot.
Okay, the larger the time scale, maybe the less informative.
I'm sorry, less what?
Less informative the method will be.
Could be. It could be.
It's to find maybe.
Yeah. I think that's a nice thing to wrap up with our application-based stuff too, because I think it goes in hand with that a bit as well. You could picture botnets having a certain communication time window. You could picture other types of applications being more visible in whatever structure is being shown here on different time windows. So it's a good question.
Okay, we're out of time, so thanks very much, Eric.